Right, now we're going to start talking about some of the graphs of these equations. And so I think I'm going to kind of start you off with this little library of parent functions that you can think about, and then we'll see that in general other polynomials of the same degree will look more or less the same. Okay, so we're going to start off with y equals x cubed. If I was going to predict what the graph of y equals x to the 3 looked like, I mean, I would think it would be kind of like the graph of y equals x squared. As x gets bigger, y gets much bigger, so it probably curves upwards like that. But if you think about what happens when you take a negative number to the third power, you get a negative number. So it might be kind of like a parabola where the like one of the sides had flipped down. And so, like that. Okay, that's not a very good sketch, but let's consult with a professional, right? Let's go over here to the TI-84 and get all this stuff out of here. This looks like we were using it for some calculus earlier. Let's graph y equals x to the third power. Oh, goodness, I need to reset my window. Pardon me. All right, there we go. Okay, and that's pretty much what I've drawn, I would say, is that we've got ourselves a graph that comes from below and goes up. Now on your sheet, it probably is going to ask you about the end behavior of this thing. Okay, and that's where we're talking about what happens in the extreme cases. Okay, so I'm going to say for this one, on the right side, as x approaches positive infinity, so is y. Y is also approaching positive infinity. That just means the farther I go to the right, the higher the graph gets. And there's no limit to that. We could make x to the 3 as big as we wanted by choosing x's that were big enough. And then on the other end, I could say, okay, leave myself some room, that as x is approaching negative infinity, y is approaching negative infinity as well. So this is kind of like that parent graph for y equals x to the 3. The next kind of natural question would be like, hey, what does the graph of negative x to the 3 look like? We know that we had y equals x squared, and then if we had y equals negative x squared, it wasn't like a square, but it would open down like that. So it would make sense that maybe this graph will get flipped upside down, but let's just go in and let's just insert a negative there and see what happens. And sure enough, okay, it's going to come from above and then go down. And that's going to mean that the end behaviors would flip. But we'll make a chart and get a general rule here in a couple minutes. Now let's talk about the graph of y equals x to the 5th. Okay, so maybe think for a second about what you would expect this to look like. And let's just have a look. Okay, looks pretty much exactly like y equals x to the 3rd. It's a little steeper on the sides and a little flatter in the middle, but otherwise it's the same. And it has the exact same end behavior. So, in that space in your notebook where it's talking about x to the 5, I mean, you can draw the picture if you want and write out the end behavior a second time, or you can just say, hey, this looks almost exactly like y equals x cubed, and the end behavior is exactly the same. But let's move on to some even degree polynomials. All right, yeah, let's have the calculator graph y equals x to the 4th for us. So, oh, whoops, I was not clicking in the right spot. X to the 4 like that. Okay, and then we're going to graph this thing, and that looks a whole lot like a parabola to me. Okay, what you're supposed to notice about this, I don't know if it's actually even big enough on your screen, is, let me draw my own sketch. Okay, that was a really bad one, but, it doesn't matter, it's just a sketch. And what you're supposed to notice about this is that it's like, it's steeper on the sides, but also flatter in the middle. And the reason for that is that if you take a number that's between 0 and 1, like what you might call a fraction, and you take it to the 4th power, it's not going to get bigger. It's going to get smaller and closer to 0. And definitely more so than had you only taken it to the 2nd power. And that's why it's closer to 0 between x equals -1 and x equals 1. But if you're interested in that, come talk to me about it. So, but the end behavior of this one is going to be different, right? Because both sides are going up, much like the graph of y equals x squared. Okay? So I'm going to say for this one, as x approaches positive or negative infinity, y is going to approach positive infinity. Okay? Just like y equals positive x squared. Now, if I went back into the calculator and I switched this to negative x to the fourth, you should expect this to look just like, the graph of y equals negative x squared. Okay, it should go upside down. And sure enough, it does. And so in that case, if we had a negative x to the fourth, then we would say that as x approached positive infinity or negative infinity, y was approaching negative infinity. But we'll, get a good rule for that here. And then for x to the sixth, I'm just going to go over here, change it, and delete the negative, but change that exponent to the 6 and graph it and be like, okay, that actually looks exactly the same as y equals x to the 4. It's not, because we know that you take a number to the fourth and you take that same number to the sixth, it's not going to be the same number, but it looks the same. So I'm just going to say, oh, hey, this is y equals x to the 6 now. It's deeper on the sides, it's flatter in the middle, and it has the same end behavior. So, on yours, you might say it looks just like y equals x to the fourth, and it has the exact same end behavior. That might be what I would say. All right, now we've gotten pretty far into this course without actually giving a definition of a polynomial, so I think now is going to be the time where we So an nth degree polynomial in x is an expression of the form, it's got a bunch of powers of x that are whole number powers. N is a positive integer, and each a value is a real number. And so like all of the x's have to have whole positive integer powers. Okay. So an example of a polynomial, we've worked with a lot of them this year. Linear equations were polynomials. So 2x plus 3 was a polynomial. Okay. Quadratics, x squared plus 4x plus 5. That's a polynomial. Higher degree objects like we're interested in today, like x to the 3 minus 8 or x to the 4 plus x squared plus 4x minus 9, I don't know, something like that. These are all polynomials. And yeah, and so an example of something that would not be a polynomial would be something where we had not positive integer powers of x. So something like maybe, 1 plus x plus square root of x. Okay, we haven't talked about it yet in this class, but that would be the same as 1 plus x to the 1/2 power. You cannot really see that, but now you can. We haven't talked about the square root of x being a 1/2 power, but it is. And it's not a whole number power. It doesn't look like one. And so that's going to be not a polynomial. Okay, another example of something that we've seen pretty recently is something like 3x squared minus 4x plus 1 plus 12 over 2x minus 5. If you recognize this, that's probably a good sign. Okay, but this is not a polynomial because of that dividing by 2x plus 5. I'm not even going to say, but that's like a negative power of x, which is not a positive integer. Okay, so I'm just going to kind of highlight the offending items here that are causing this to not be a polynomial. I could also say that, oh no. Yeah, my tablet crashed suddenly, and I don't remember exactly where I was, but I think I was about here. I had highlighted the offending pieces. Okay, now the next thing I might ask is what's the degree of a polynomial? Okay, and the degree, I've already mentioned it, is the highest exponent we see. So, for each of these things that are a polynomial, I'm going to go through and I'm going to, give the degree. So, this first thing, I only see 2x, and that's x to the first power. So I'm going to say that's degree 1. Okay. I see x to the 2 right here. So that's going to be degree 2. Okay. Over here, x to the 3 is the highest exponent I see, and that will make this a degree 3 polynomial. And then over here, okay, the biggest exponent I'm seeing is x to the 4, and that will make this a degree 4 polynomial. Okay, in this class, in Algebra 2, we're mostly concerned with degree 3 and 4 polynomials. I think occasionally degree 5, and sometimes for the just sake of interesting problems, maybe a little bit higher. But on the tests and stuff, you should expect mostly degree 3, degree 4, maybe a little bit of degree 5. Okay, now I think now would be a good time for us to just get our general rule for the end behavior of a polynomial function. But I'm realizing there's something I haven't told you about yet. So the leading coefficient, you're going to hear me use that word quite a bit. The leading coefficient of a polynomial is the number that's attached to the highest power of x. Okay, so on 2x plus 3, the leading coefficient is 2. Okay. On x squared plus 4x plus 5, the leading coefficient is 1 because it's 1x squared. Maybe I'll change this to 1/2 x to the 3 minus 8. In that case, the leading coefficient would become 1/2. And with this last one, I don't know, maybe I make it negative x to the 4th plus x squared plus 4x minus 9. In that situation, the leading coefficient would be -1. Okay. Now in this class, we're mainly interested in whether the leading coefficient is positive or negative, not really the value of it. But we will be interested in what that can tell us occasionally. All right, so the general rule for end behavior really splits up on whether you've got an odd degree polynomial or an even degree polynomial. Okay, that's the key aspect, is what's the degree and is that degree even or odd? And within that, we're going to kind of split this up into the case where we have a positive leading coefficient and where we've got a negative leading coefficient. Oh man, I can do better than that. Give it one more shot. If that doesn't work, I'll have to pause. Oh, that's much better. Okay, so I'm going to say positive leading coefficient first. Okay, and I'm just going to ask you to remember what you already know. Okay, think about the graph for odd degree, think about the graph of y equals x cubed. Okay, so if it's a positive leading coefficient on an odd degree polynomial, it's just like y equals x cubed, which we just saw went like that. Okay, and so that's going to be as x approaches positive infinity, y approaches positive infinity, and as x approaches negative infinity, y is approaching negative infinity. Okay. And then for a negative leading coefficient, I'd say it's just like negative x cubed. So as x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y is going to positive infinity. And then with an even degree polynomial, I just want you to think back to y equals x squared. That's a graph that we know what it looks like. Okay, so that goes up on both sides. That was a really bad parabola, but you know what it looks like better in your mind than you can draw. So I'm going to say as x approaches positive or negative infinity, I only need one because it's doing the same thing, y is approaching positive infinity. And then for a negative leading coefficient, we're thinking just like y equals negative x squared. Okay, and this is the first time that we've needed to deal with infinity in this class, but I'm going to tell you, just like I tell the students in my calculus class, this will be the first time I'll tell you, and it probably won't be the last, especially if you wind up in my class again in a later year, but infinity is not a real number. And you shouldn't be treating infinity like a real number. So you can't be saying like x equals infinity or y equals infinity, anything like that. All we can say is as one thing approaches infinity, something else approaches maybe an infinity or something else. Maybe later on in the course. But don't say anything equals infinity, because that's not possible. Equals is a relationship between two real numbers. All right, now let's talk about y-intercept. Okay, we've talked about this a few times in this class. A y-intercept of a function, maybe we've got some sort of like interesting looking function, y equals f of x. Okay. The y-intercept, that's the point that corresponds to x equals 0. Okay, so I'm going to say that the y-intercept, that's just given by f of 0 if we're graphing y equals f of x. So for example, if we had f of x equals 3x to the 4th plus 4x to the 3 minus 2x minus 1, and we needed to plug in x equals 0, well, I'd be saying, okay, f of 0 equals 3 times 0 to the 4th plus 4 times 0 to the 3rd minus 2 times 0 minus 1, which is going to be equal to -1. And if g of x is equal to 4 plus x to the 2 minus x to the 3, Well, and we went to find the y-intercept. That would be g of 0 is 4 plus 0 minus 0, which is just 4. So what I'm pointing out here is that the y-intercept is given by kind of the constant in the equation for a polynomial. So let's start to sketch some graphs. Okay, so let's just sketch some graphs that might have a slightly different y-intercept. So the graph of y equals x to the 3 plus 5 is going to look just like the graph of y equals x cubed, except the y-intercept, instead of being at 0, y equals 0, it's going to be at y equals 5, so it's going to move up by 5. So I'm going to go in here and I'm going to draw. Actually, maybe what I should do is draw my idea of what I think y equals x to the third looks like. That might be a little too flat, but that looks pretty good to me. And then come in with a y-axis after the fact. Okay, so that's going to be right there at y equals 5. And then draw an x-axis to fit. Okay, and then I'm going to do the same thing for x to the 4 minus 2. Okay, x to the 4, it's kind of like y equals x squared, except it gets pretty steep pretty quick. Not ever been very good at drawing that half. Okay, that's going to have to do. Okay, that's my idea of y equals x to the 4. And so in y equals x to the 4 minus 2, it's going to have a y-intercept of negative 2. So it's just going to have moved down by 2, with respect to the regular y equals x to the 4th graph. So if this is at negative 2 down here, then the x-axis would belong there. All right, with these two, okay, I'm going to say, all right, negative x cubed, that looks kind of like that. And negative x cubed minus 3 would just be down by 3 from the regular negative x cubed. And so, like that. And then 1 minus x to the 4th, that's like negative x to the 4th plus 1. So this is going to be the type of, it's going to be like a negative x to the 4th, so it's going to look kind of like a parabola, but flatter and then steeper. I think that might be too steep, but it's all right. Okay, this is just a sketch. Okay, and it's got a y-intercept of positive 1. So I'm coming through here, and that's at 1, so, maybe the x-axis is down there. All right, now let's sketch some more interesting graphs. So that's where we're going to connect the factoring and the sketching. And so I'm going to just kind of show you, we're going to take the kind of the same set of steps each time. We're going to always start by factoring the polynomial. So I'm going to say, okay, look, y equals 2x to the 3 minus 2x. I can factor that. That's going to be 2x times x squared minus 1. Okay, I can factor this more. Okay, what we learned in the last unit was that the factors corresponded to zeros. And we actually saw it in the previous unit too, when we were studying quadratics. So I know that this polynomial is going to have zeros at x equals 0, x equals negative 1, and x equals positive 1. So I'm going to draw a little x-axis here, and I'm going to label those zeros. Okay, negative 1, 0, and 1. Okay, moreover, because they're zeros of the function, I know that these points right here are on the graph of 2x to the 3 minus 2x. That's going to be big for us. Okay. Also, I know the end behavior because this is a third-degree polynomial with a positive leading coefficient. Okay. So it's going to look like y equals x cubed. So that means it's going to come from below. So you're going to want to start with the end behavior. It's coming from below, and then it's eventually going up. Okay. And then you need to use the fact that I'm just going to tell you that polynomials are continuous and smooth. So they're not going to have any like sharp corners or like broken graph or anything like that. So if it's coming from below and it's got to pass through this point and come back to, this one right here, then it's going to have to go up and then turn around. Okay, and then in order for it to pass through here and then go back up and catch up with this end behavior up here, we're going to need to go back through like that. Okay, and that's going to be a suitable sketch for our purposes. So I'll do one more for you, and then, actually, no, how many do I have? I've got 3 more to do for you, but maybe I'll only do 2 of them, and I'll let you try on your own for the 4th. So this x to the 4th minus 5x squared plus 4, we've already factored that in. All right, so we already factored the ones. I just copied in the result, and I'm going to go over here on an axis. So negative 2, negative 1, 1, and 2. And I know that negative 1 and 1 have more distance between them than 1 and 2, but what I've found is that when sketching these graphs, if you try to make it proportional, your graph gets all out of proportion. It doesn't look very good. So I found that this is the way to make the best looking graphs. So this is a 4th degree with a positive leading coefficient. Okay, so I know that it's going to look like y equals x squared, which is to say it's going to come from above and then eventually go back up. Okay? And then these are all zeros. And today, all of the zeros that we're interested in are zeros where it's just going to like pass straight through. We'll talk about times where it doesn't pass straight through in the next lesson. So for now, it's just going to go straight through and then straight through again and then one more and then up there. Okay, and so it kind of looks like a W. And what I'm going to point out also, I almost forgot to mention this, is that, okay, a 3rd degree polynomial can have at most 2 turnaround spots. And a 4th degree polynomial, I have a better name for those turnaround spots, but for now that's what I'm going to call them. And a 4th degree polynomial has at most 3 turning around spots. Okay, so I'm just going to throw that out there. Oh, and also, if you were asked to, show the y-intercept or something, then maybe you could, go after the fact. That's what I recommend, drawing in the y-axis later. Okay, so in this one, it would be, halfway between negative 1 and 1. I'm not totally certain. I think it is probably at that maximum, but you don't have the tools to know that. Determining the locations of, these turnaround spots, that's exactly what calculus is. All right, now I think this is going to be it for this video. I'm going to do one more for you, but this is already really long, and we've done a lot of examples, and so I think this is going to be good enough. But we haven't sketched 3rd degree with a negative leading coefficient, so that's what I'm going to do. Okay, and I changed it a little bit from what's written in your notes, but I hope you'll forgive me. So we're looking at y equals negative x to the 3 minus 5x squared minus 6x. My advice in general, when you're trying to factor something that's got a negative leading coefficient, factor out the negative. Okay, you've been trained your whole life to factor, kind of with the assumption that the leading coefficient is positive. So why not just factor out the negative and then look at it? Oh, wait a second. There's also another greatest common factor that x is common to all 3. So I'm going to factor out the negative x. And then all of a sudden, oh, hey, this is a quadratic that I'm able to factor. Okay, and now, I forgot to mention that, I don't know why I can't scroll down at all. This is a 3rd degree polynomial with a negative leading coefficient. Okay, so I know it's going to look like the graph of y equals negative x cubed. So I go in and I'm going to sketch my x-axis. I've got zeros at x equals negative 3, x equals negative 2, and x equals 0. Okay, remember, I'm gonna always equally space out my x values, and because this is just a sketch. We're not given a piece of, hey, produce the most accurate sketch you can. We're just sketching to see what we're looking at here. What's the shape of the graph? Really is the idea. Okay, so y equals negative x cubed is going to come from above, and then eventually go down. Okay, these are the zeros, and I know the graph is going to contain all 3 of these points. Also know that it's just going to pass through on all of them today. Okay, that was not intentional. Let's see if I can try that again. All right, there we go. And that's a pretty decent sketch. And not as good as the TI-84, but, better than you probably could sketch a 3rd degree polynomial before you watch this video. All right, that's going to be all for today. Thank you for watching. I really hope this helped.